Welcome to the lecture on Ethereum. So, Ethereum is, well, it's not that new as a blockchain, but at least it's newer than Bitcoin, 5 years newer. So, Ethereum is nowadays being used for a lot of other applications other than cryptocurrencies. So, at least as of 2022, when I'm recording this video, Ethereum has become a default mechanism for all fintech transactions. So, a brief look at the history. Dwork and Naur proposed the idea of proof of work, which was way back in 1992, where the basic concept behind proof of work was that to you just cannot be a passive participant in an algorithm, right? So, when you say that a certain transaction is valid, or let's say a certain account has a certain balance, you need to do some amount of work before you can actually say that. So what does this ensure? This basically ensures that if 51% of all the nodes or 51% of the work that is done is honest work, you can guarantee that the blockchain, even without permissions, will still work. So it took some time. It took 11 years for Vishnumurthy and his group to use the proof of work to secure a currency, in the sense that from 1992 to 2003, the idea of using this for cryptocurrencies had not gained a lot of traction. Then Bitcoin came in 2008, courtesy Satoshi Nakamoto, but again, that's not the name of a real person, it's a pseudonym. And then we have seen a deluge of cryptocurrencies. So, as we talk, there are a lot of cryptocurrencies, people actively buy them, sell them, buy futures, contracts, hedge on them, and so on. So, Ethereum came in 2013, it had a different design philosophy. So, unlike being made by one person, it was initially proposed by Vitalik Buterin, but then many people like Gavin Wood and so on, all of them came in. So now it's a big group that actually manages Ethereum. It's much more than a digital currency. So if you think about it, it has generalized the idea of a digital currency. So when we transfer some money from one account to other, so we have account A and account B. So when we transfer some money here, effectively we are computing the new balance as A minus X, where A is the amount of money transferred and B is equal to B plus X. But of course, it is not as simple as this, because then we are seeing that if the new balance is less than zero, which means the transaction is not valid, then we will restore A to what it used to be, right? And the transaction is not valid. So if you see, for transferring a small amount, we actually need to run a piece of code like this. So even a basic money transfer is actually the execution of a code, and this code can be generalized in the sense you can say that, look, I will transfer 10 units. In the case of Ethereum, it's 10 ethers. If the balance is less than 50, otherwise I'll transfer 5. You could say that. So all such pieces of code are known as smart contracts. So that is why Ethereum, at least as of today, is much more than a digital currency, because it allows users to run arbitrary code on a shared global state. What is a shared global state? It is the state of all the accounts. That is the shared global state. As of 2018, it is the second largest cryptocurrency in terms of market capitalization. And now, of course, I don't have the 2022 numbers, but as of today, it is by far, the most popular after Bitcoin. And it's being used for doing a lot of other things as well, like create financial products, including managing digital art and collectibles. So this also can be stored on the blockchain, right? So this idea over here is non-fungible tokens. So we'll see what they are as we keep discussing. But before I go further, I would like to say that the entire discussion on consensus, the entire discussion on Bitcoin and blockchains is a prerequisite for this chapter. So kindly go back in the playlist, look at all the discussion on consensus, bitcoins, and blockchains, and then kindly come back, because otherwise you'll not be able to follow the material. So the idea is we have a world state, which as I said is a state of all the accounts, right? So unlike Bitcoin, which didn't have the notion of accounts, Ethereum has the notion of accounts, and all of these accounts together comprise or form the world state. Then, of course, we have multiple machines. So each machine then has a state of its own, a local state, which is the machine state. But mind you, any modification that is ever done is done to the world state. And unlike a traditional cloud-based system, the world state is actually not present, in any dedicated cloud machine. Instead, either the entire world state or parts of it are replicated across all the machines. So as we know in all blockchain-based systems, each machine essentially contains the entire state. That is probably one reason why blockchains were not popular in the earlier days, right? Prior to 2015, because machines didn't have the kind of storage to at least store the world state. But now this has changed. So every machine will have its private state, but the private state is valid insofar as the scope of the currently executing transaction. So now let us move on. So the basic concepts in an Ethereum are like this. So an Ethereum is a blockchain. The blockchain starts with a Genesis block. So a blockchain is like a linked list. It starts with a Genesis block. So Bitcoin was the same as well, and we group transactions into blocks. So the blockchain pretty much contains all the transactions that are happening in the Ethereum ecosystem. So as we have discussed, every machine maintains some state, which is either a slice of the world state and some internal private machine state as well. There are two kinds of functions that each machine can apply onto the world state. So the first kind are state transition functions, as we have seen, which is basically transfer some money from account A to account B, right? So that is one kind of a state transition function. So this is basically changing the state of the world. Why? Because we are changing the state of account A and account B, because we are changing the balances, right? So this is a state transition function. The other is an account creation transaction. So in this case, what is happening is that we are creating a new account, and every new account also has some associated code with it, in the sense that every state transition is simulated as a message call. So in this case, if let's say account A wants to add some money into account B, it will send a message to account B, and account B will have some code associated with it which will process the message, right? And this code was initially made a part of account B by the account creation transaction. So that code will see that, okay, new money is coming in. What do I need to do? This is what I need to do in this case. So basically, let's say B dot balance is plus equal to X, where X is the amount. So Ethereum has a built-in currency the same way we had, currency in Bitcoin. The lowest denomination is a way, and many a time we actually, the protocol relies on the lowest denomination, which is a way, one way. And then, of course, as we can see, we have some very large denominations, which are actually much, much larger. So 10 raised to power 12 ways. So 10 to the power 12 ways is a Sabo, 10 to the power 15 ways is a Fini. So incidentally, they are all founding members of Ethereum. And 10 raised to power 18 ways is an Ether. So we will see that the term Ether is being used quite a bit later on. So the world state is like this. So the world state, if you think about it, is a simple mapping where every account is represented by its address, which is a 160-bit ID, and that is mapped to the state of the account or the account state, right? So you have an account number and an account state, and this can be extended to be a generic mechanism. It's not the case that every account needs to have some amount of money or ethers in this case. But it could contain anything. It could contain digital art, for instance. It could contain insurance products. It could contain, anything that you want. So here the key point is that the account states have to be maintained by each machine. In the sense, every machine has to maintain a database. So this is quite similar to Bitcoin, but it is just that Bitcoin didn't have the notion of accounts and Ethereum has the notion of accounts. Furthermore, the protocol suggests a data structure, the Merkle Patricia tree, which we will look at, to maintain the state database, which is nothing but a large database of key value pairs, basically. And so we'll have similar data structures. So we had a Merkle tree in Bitcoin, if you think about it. And we will have something similar over here, such that the contents of the root node are dependent on the state of the entire tree. So we will use this as the same concept. We will use this as a common concept for looking at the account states of Ethereum. But essentially, the way that we perceive the world states of Ethereum are a set of key value pairs. All right. So, what is a Merkle Patricia tree, or it's also called a trie? So, let's understand what is a trie. So, a trie or a Patricia trie is a data structure which is used to store a bunch of strings. So, as you can see, let's say if the bunch of strings that I have are as, to, and let's say te and do. The way that I would actually store them is that I will start from the root node over here, which is over here, and create a prefix tree. So, the prefix tree. So we will look at the first letter over here, match that with the first letter over here. If A and A match, then we come here, and then again S and S match, so we come here. And similarly, we look at TO and TE. So what we do is that we create a prefix tree over here. And so basically, the idea is that the trie is a representation of the prefix tree where if we want to find if a given string is there or not, then all that we do is we start with the first letter and we traverse it. Optionally, this can be used to store key value pairs. How do we do that? Well, we use the same idea. We treat the keys as strings. All the strings are stored in the prefix tree like this, and the values are at the leaves, right? So the values are where a full string for a key terminates. So the values are at the leaves over here. So as you can see, a Merkle Patricia, in this case, sorry, a Patricia trie can be used to store key value pairs in this fashion. What is a Merkle tree? So we have seen this in the case of Bitcoin as well. So it is basically used to store a hash of a bunch of data, not one datum, but a large amount of data. We want to store a hash of it, such that if there is a small change, and there are n data items, it will take order log n time to propagate the updates. So in this case, what we do is that we take a data item with value A, we hash the item. So we call it hash A. And similarly, we create a tree like this where the individual data items are B and C. We create a hash value, hash BC. And the root, basically, so what happens is every node contains the hash of its children. So this node contains the hash of A, hash BC contains the hash of its children. And the root furthermore will contain the hash of the concatenated value of hash of A and hash of BC, right? So in a sense, the contents of the root represent the state of the entire tree. So this is not a trie, this is a tree. The earlier one was a trie. So this is the state of the entire tree, and the state of the entire tree is represented over here in the root, the contents of the root. So if anything changes, then of course it will be very easy to propagate the new change to the root in roughly order of log n time. So the Merkle Patricia tree is like a union of both the ideas, a Merkle tree and a Patricia tree. The leaf nodes are the key value pairs, and they can be used to store anything. For instance, the key can be the account ID or the transaction ID or even hashes of them. But the key point is that whatever we consider the key, anyway, the MPT tree doesn't care. The key is used to traverse the MPT tree the same way you would traverse a Patricia tree, right? Exactly in the same way you would traverse the tree. So that is what the key is used for. And we traverse it a nibble at a time. So let's say if it's an 80-bit key, for instance, then we divide it into into 20 nibbles. What is a nibble? A nibble is 4 bits. So what we do is that we divide it into nibbles. We will have 20 such nibbles, and it will basically be a 20 level tree, and we'll traverse it a nibble at a time. And every node, because we are dealing with in terms of nibbles, will have 16 possible children. So every branch node in the tree will have 16 possible children over here. But there is a catch. So the catch is that if you look at it, who wants a 20 level tree? That's too much. So many a time, a large part of the value space will be sparse. If the value space is sparse, the MPT construction in Ethereum discourages nodes with a single child. So it discourages any kind of an internal structure like this, right? It is a much better idea that you know, if this is the internal structure, then this actually points to this point where this is a fused node. So the fused node basically will indicate what are the values, additional values of nibbles in this chain over here. For example, let's consider hex values. So if this is A and let's say this is 5 and this is 6 and 7, so we'll basically create one fuse node where we will store the fact that, well, we enter it using the A edge, and all the children for this position have 5, and then of course, and after that we can have branches. So this fuse node is called an extension node, right, which is collapsing the chain of nodes into a single. So what we will have after this is we'll have this as an extension node. We'll store 5 over here, and then again we'll have two of these children over here, 6 and 7. So the value space is expected to be reasonably sparse, so that is why we'll have many of these extension nodes in the MPT tree, which will reduce the storage and as well as the traversal time substantially. So this was a try part, this was a try aspect, the PT part of the MPT tree. But also what we do is that we have the same idea that an internal node stores the hash of its children, so on and so forth. So we create what is called a root hash, which is basically the hash stored at the root. And the way this is done is that we traverse this. So basically we, in this case, we treat the Patricia tree as a Merkle tree. We traverse it using DFS. We compute the hash. Every parent computes the hash of its children, and then finally we have the root hash. So the advantage of doing this is that if, let's say, at any point there is a change, then incrementally we can update the root hash. We don't have to traverse the full tree. So we just compute the new hash for the internal node and kind of propagate it up. So this is why we have a Merkle Patricia tree where it is easy to add a node, it is easy to search for a node, as you can see. So this acts like a search tree as well. It's kind of compressed because of these extension nodes. And furthermore, we maintain internal hashes as well as the root hash. So this completes the definition of the Merkle Patricia tree or the MPT tree. So the MPT tree is quite important in Ethereum because it is used to store many things. So what are the things? So given the account, right, mapping it to the account state is anyway what the world state is, right, which is nothing but a mapping from account IDs, 160-bit account IDs, to the account state, right? So of course we store several things as a part of the account state. So the word nonce will appear many times in Ethereum, and every time it will mean a different thing, unfortunately. So in account state, the nonce basically means the number of transactions that have been sent to an address, right? Either that is this, the number of transactions that have been sent from this account, or the number of times in this account you have created a new contract. A contract is a piece of code basically. Balance, that's easy, the number of way owned by the account. Storage root, So the storage root is where we actually store the state of the account, and this is again stored as an MPT tree. So the root hash of the MPT tree is known as the storage root, right? And so this stores the contents of the account or several accounts. The code hash is nothing but we take all the code that is associated with the account. So this code is also known as a smart contract, but we'll refer it to as just code in this presentation. So this code is anyway targeted towards something called Ethereum virtual machine, which is like a virtual machine which is meant to run Ethereum code regardless of the platform. So the hash of that is known as the code hash. So how do transactions work? So the way that transactions work is that a message is transferred from one account to the other, and the other account processes it. Right? So what is there in a message? Well, we can have structured data and unstructured data. So the unstructured data, the field is data where you can send anything, function arguments, anything that you want, absolutely anything that you want can be sent over here as a part of the message transfer, which is the data field of the message transfer. So as we have discussed earlier, there are two kinds of transactions in Ethereum. There is a message transfer, and we can also create a new account or contract creation. In that case, what we will have to do is, so since every account will have some code associated with it, what does this code do? Well, the code is invoked when a message is received, right? So when the account receives a message, could be any message, could be credit yourself, debit yourself, could be anything. In that case, the code that runs is known as the body, and this code has to be part of the account creation or account initialization process. There are a few more fields. So we have seen nonce. So nonce here is also the means the same thing, but as I have said, we will see the term nonce appear in several places and will mean different things. So in this case, it's a number of transactions sent by the sender. So we have two very interesting things in Ethereum. So let me explain the motivation behind them. So what is the key point? The key point is that everything in Ethereum is being monitored as code execution, including transferring money. Because as I've just said, transferring money is not that simple. Basically, because you'll have to run a small program at the sender side, a small program at the receiver side. So the issue is that now we need to provide an Ethereum virtual machine to run the code as well as a language for the code. So when you're running the code may go into an infinite loop. There may be faults with the code, all kinds of issues that happen with code. See, even though the language that runs on the Ethereum virtual machine is Turing complete, we still want to charge a premium for the amount of code that executes, in the sense we don't want people to write very heavy code, right? So that will slow down the entire Ethereum system. So we define the notion of gas. So gas actually stands for gasoline. So they call petrol gasoline in the United States. So basically per computational effort, or known as gas, the number of VE we need to spend. So what happens is that as code keeps on executing, depending upon the instructions you're executing, how much memory and storage you're using, gas continuously gets deducted. So the idea here is to basically create code which will not use a lot of gas. Then there is a gas limit. So the idea of the gas limit is that, look, if you have said that you will use 20 units of gas, you can't cross that. Crossing that basically means you may be moving towards an infinite loop, and we don't want the system to hang. So the moment you run out of gas, the transaction stops. Furthermore, for the node that is initiating the transaction, it needs to actually pay. So the idea is that if you want to initiate a transaction and you want Ethereum to accept the transaction, you have to pay the gas price multiplied with the number of gas units that are actually spent. But since an upfront payment is being made, and at the moment we don't know how much of gas will be used, so whatever is the maximum gas amount that you are saying, multiply that with the gas price, pay it upfront. Later on, a refund will be issued if less gas is used. Then we have the standard fields. 2 is the recipient of the message. And because Ethereum was still has its cryptocurrency DNA, it does have value as a common field where you're referring, where you're kind of using it to transfer value. But if the Ethereum blockchain is being used to implement something that is not a cryptocurrency, then we need to use the data field where arbitrary data can be specified. So the key idea again is that we have accounts, we have messages that are sent from accounts, and clearly in the case of currency, these are credit debit kind of transactions. But as I said, Ethereum scope goes well beyond that. So let's now come to the block. So as we have seen in Bitcoin, a block basically contains a bunch of transactions, contains a list of transactions along with other information. So here is the fun part. Unlike Bitcoin that actually always stored a linked list, in Ethereum you kind of store a DAG. So you basically store the fact that, well, this could be the longest chain. So we will again discuss what is the longest chain in some detail. But it is very well possible that at some point of time, other nodes tried to add their blocks, but they were not successful in the sense that they were not, they were not part of the longest chain, right? So Bitcoin used to just discard them, but in this case, we don't discard them. In case you lose, you still get a consolation prize. So what you do is that Ethereum kind of maintains a truncated DAG where this could be the longest chain. So we will define what the longest chain means at a later point. But again, there will be a few of these blocks which were not a part of the longest chain but did get added at some point. So what we will do is we will remember them and we will compensate them for the effort that was put in. So such blocks are known as omers. So omer is basically a gender neutral term for uncle or aunt. And so we will refer to omers as uncles. So if you see if this is the block, then an omer is basically a sibling of its parent. It's still not on the chain that is validated. It's still not on the blockchain. But the fact is that an unsuccessful attempt was made to add the omer to the grandparent. But since the parent won, the omer got kind of thrown out. But the good thing here is that once this block is successfully mined and added to the chain, we will kind of be nice to the omers and give them a small amount. So a small amount of currency will be given to them, kind of like a consolation prize. So this has advantages in terms of preventing starvation and so on. So what are the list of fields in a block? So of course we'll have a bunch of transactions, but we have a lot of other things as well. So of course we have a hash of the parent's block header. So this is what makes the blockchain a blockchain, because every node in a blockchain contains the hash of its previous node. So if this is the node, this is its parent. The moment you store a hash of this becomes a blockchain. We also maintain a list of omers. So we store the hash of the list of omers. A beneficiary, in the sense, if you successfully mine the block, who gets the fees, right? Then we will have a bunch of MPT trees. So we'll actually have three. So the MPT trees over here are known as state root, transactions root, and receipts root. So state root basically means the root hash of the account state, right? As simple as that. That if I take the world state and then I take its root hash, then I am linking a block with the root hash of the world state to indicate that once all the transactions for this block are processed, this is the world state. And given that the world state itself is stored as an MPT, it is very easy to kind of get a handle to the world state, which is the root hash of the trie. Then furthermore, a block contains a bunch of transactions, so which are also stored as a trie, where again the key is the transaction ID and the value is the content of the transaction. So in this case, we have this. So mind you, this was there in Bitcoin as well, right, in a slightly different form, but the idea here is the same. So the idea here is that the machines store the state, in the sense they store an exact list of transactions and the world state and so on. But what actually is there in a block is basically the root hashes. Once a transaction executes, right, the code finishes executing, It will generate some return value and some logs. So that together is known as the receipt. That is again stored as a trie, which is basically again the key value here is the transaction ID and the transaction receipt. So the root hash of that is also stored. Furthermore, what happens is if you actually think about it in an Ethereum account, a lot of code runs. So it is possible that there may be bugs in the code, maybe it didn't run correctly, maybe it had issues, exceptional conditions, and so on. So in this case, we would like to store logs. So logs again are defined by the code, but essentially what you store is you store a log topic and some sort of a checkpoint on the machine state such that you can kind of go back and debug. So this is stored in a data structure called a Bloom filter. So we will discuss what is a Bloom filter in some detail in a subsequent slide. But the key idea is that some debugging and checkpoint information is stored in the block because the block is after all associated with executing code. So it is important for us to understand if something went wrong, where did it go wrong, and store enough debugging information, including checkpoints and watch points, right? So this information is stored. We have few more fields, and all of these fields, trust me, are very important in a block. So difficulties. So this is related to the proof of work concept in Ethereum. So I will not discuss a lot about this right now because we'll get some amount of time later on to discuss what is difficulty. Let us say that it indicates how difficult it is to mine the block, or mining the block basically means adding it successfully to the chain. So we will see that this is a varying quantity and it is dependent on the previous block and the timestamp and so on. But let's discuss this later. The number is important. It provides the depth of the block starting from the genesis block. So if the genesis block is numbered 1, the next one is 2, 3 and so on. So that's how you decide the chain, right? It's a blockchain, right? So every block has to have a number starting from the beginning. Gas limit we have discussed is the total amount of gas that can be used, and gas used is the amount of gas that we have used already. So gas used has to be less than equal to gas limit. Timestamp is the time value at which the block was created. It is a Unix time value at the block's inception. In addition, we could have additional metadata because, as I have argued, Ethereum can be used for all kinds of applications. So many a time, the application would need some additional data of its own. So that feature has been provided. Then we have two more parameters, mix, hash, and nonce. So in this case, nonce is not the number of transactions sent. It is something totally different. We are still using the same term, unfortunately. So both of these are used to mine the block. So both of these are used in block mining in computing the proof of work. So we'll discuss this later. But kindly remember these things as mix hash and nonce to be discussed later. The mix hash, by the way, is a 32-byte quantity, and the nonce is a 8-byte or 64-bit quantity. So let's now come to some things that we have discussed but decided to talk later. So we will discuss transaction receipts and the Bloom filter. So as we have seen, every transaction modifies the world state and may optionally produce an output. For example, you may ask Ethereum to compute the result of some function. For example, find out how many accounts are there whose balance is greater than 100 ethers, for instance. So that can come out here. So the outputs of the transactions, the receipts are again stored in a trie, and the root hash of that trie is stored in the block. So let's look at what are the transaction receipts that we look at. So that will have the set of logs that were created for debugging. The post transaction state, in the sense after the transaction, what was the world state, the gas that we used, and a dedicated data structure called a Bloom filter to store the logs, right? So store the debugging logs. So in this case, the hash of the world state will act as the key in the trie to basically find out the transaction receipt, right? So you say that, look, if this is the world state after a transaction, give the receipt to me, and the receipt would include all of these things. Let's now look at a log entry. So log entry is kind of interesting. And the key part of the log entry is that this is what is produced by machines while they execute transactions, such that later on an Ethereum client can query the log entries and find out if certain logs were generated, or let's say for a certain log topic. The log topic could be, you are printing a message, right? So message for what was actually presented, what was actually printed. So this could be done. So the log entry would consist of three fields: who's the logger, what are the list of log topics, and what is the log data. So what we do is that if, let's say, you want to search, have some sort of a data structure to give us a yes no answer with regards to whether a log topic is there or not, right? So whether a log topic is there or not, basically yes no answer. We'd use an indexing data structure known as the Bloom filter. So what we would do is that we will compute a 2048-bit hash of this entire thing using a hashing algorithm, and we would take a 2048 entry array, right, where each entry is 1 bit. And so let's say the value of this is 1117. We'll go to the 1117th entry over here and set it to 1. That would basically indicate that for these exact contents I hash it, and then this entry is 1. So what is the probability that another uh, you know set of logs are hashing to the same entry? Well, that is 1 by 2048, which is fine. If the number of transactions is limited 32 to 64 in a block, then this is a risk that we can take. And so this will basically tell us that for, let's say, a given log, is it present in this block or not. So Bloom filter, even otherwise, is a very standard data structure which is used to find out whether a certain piece of information is there or not. Now let's come to gas and payment, right? So we have seen gas price and gas limit. So what happens is that so this, why was this done? The reason that this was done was to ensure that nobody monopolizes the CPUs in Ethereum, because every transaction in Ethereum has to be validated, which means you have to run the code. We don't get into infinite loops, so that is why the entire amount, which is the gas price multiplied with the maximum amount of gas that can be used for this transaction, right, plus a given value is plus the value, not the given value, plus the value that is going to be transferred out of the account. This entire amount is deducted upfront at the beginning of the transaction, right? Such that we always have enough money and gas with us. And let's say we didn't spend gas limit, but we spent gas limit by 2. The unused amount is later refunded. And given the fact that we are in a blockchain kind of setting, the implicit trust is there. So we will discuss trustworthiness issues. But the main advantage of using Ethereum is that as long as a majority of the nodes are honest, you will ensure that you will get back the refund. Clearly, if the transaction initiator increases the gas price, it will provide a much higher incentive to mine. Why? Because the incentive that miners get has been tied to the gas price. So higher is the gas price, more will miners actually mine the transaction and make it a part of a block. So this basically means that if you want your transaction to get in, you better pay for it. And how do you pay for it? By increasing the gas price. That will ensure it will get added to the blockchain sooner. Now let's come to the transaction execution. So what we have seen, every transaction maintains a substate. Right, along with its execution state, it maintains a few other things. So what it maintains is a self-destruct set, which is a set of accounts that will be destroyed after the transaction completes. So most of the time, a transaction may say that, look, let me finish, and after I am done, you kindly destroy this account, or you go and destroy some other accounts. So for example, one such transaction could be that go to all the accounts of students in a school, transfer all their money back to the school, because that could be their safety deposit, and it could be the graduating batch. So then we destroy their accounts, so all their accounts will then enter the self destruct set. We have seen the set of logs that could be generated and how to index them with a Bloom filter. And of course, the refund balance, which is the amount of ethers, the amount of money, virtual money, that needs to go back to the transaction. So, why have this notion of gas? Well, as I said, it places a limit on the computation that miners need to do. Because every node in Ethereum, or at least a majority, have to successfully mine the block. Mine the block means validate the block, validate all the transactions in the block, and run the code associated with them. So system remains responsive, does not enter an infinite loop. And if you run out of gas, the state needs to be reverted back because it's a transaction. There's an all or nothing transaction. So refunds are issued. And because we are in an Ethereum like setup, it is guaranteed that the refunds will always be issued correctly. Now let's come to the basic idea of message calls, right? How does that work? So along with every account, there is some amount of code with the account. And you could have one function or you could have multiple functions, but you'll at least have one. So that is the associated code with the account, which is known as a smart contract. So why is it a smart contract as opposed to a dumb contract? Well, a dumb contract is something that you can say that you can decide to kind of rescind yourself from the contract, right? But in this case, what happens is that something gets added to the chain only if a majority of nodes agree. So once an account has been added and its associated smart contract has been added, the moment a message goes to it, the code of the smart contract has to execute, because again you are assuming that a majority of the nodes are honest. So they will do this on their own and it will ensure that all contracts are honored. That is why it's a smart contract. So the message will contain what? It will contain the usual stuff: the sender, the originator of the transaction, the recipient, the available gas, the value that needs to be transferred, the gas price, additional inputs, and the call stack. Why the call stack? Because it's possible that one account can send a message to another. In response, a few more message calls can be made. So we will have a call stack in this fashion, and the call stacks, of course, have to have a finite depth, bounded depth. So all the code that we have been talking about will execute on the Ethereum virtual machine, or EVM, which per se is a Turing complete machine, right? So Turing completeness is something that is studied in computer science, which means it is as powerful as a Turing machine. In informal terms, it can execute anything. But there is an important caveat over here: it's a bounded Turing machine because we have the notion of gas. So we can't have unlimited amount of computation. So the word size over here in the Ethereum virtual machine is 32 bytes. So that is our minimum granularity in memory. The maximum stack size is 1024 entries. So it's not very large. So it's not meant for huge computations. For storage, we have an independent array of words where each word is 32 bytes. And the code as such is stored in a read-only memory or a ROM region. So it's not a classical von Neumann machine, but the code is stored in a place, so the code cannot be dynamically modified, right? So it's not a JIT kind of code. The code is static. It doesn't change. So when is gas charged? So what happens is that we have some fees which are intrinsic to the operation. So which means that for every instruction in the code, so the code basically is executed instruction by instruction. Every instruction has a certain gas price in ways. So as we keep on executing, we keep on accumulating gas. Furthermore, if there are some big calls like message calls or contract creation, calls of that type, then what we have is that we have a much bigger payment in terms of gas. Along with that, if we ever ask for more memory, more than what is initially given or provided, we ask for an increase in the amount of memory that is provided to us, then also additional gas is charged. The issue with storage is kind of tricky. The reason is that if we use more storage, of course, we need to pay for it. But again, if we kind of free storage, the amount is refunded back. So overview of the execution. Well, the execution, there is nothing spectacular about that. The EVM is a regular sandboxed execution environment which is kind of isolated from the host, so that ensures the safety and security. Whenever there is an exception of any kind, the EVM stops, and an exception could also be when the gas used exceeds the gas limit, then also you stop. Machine state, as I said, is maintained. Machine state in this case would be the amount of available gas, the current program counter of the code, the contents of the memory, right? The number of active words in memory and so on. So we measure everything in terms of 32-byte words, and of course the contents of the stack. So that is the machine state. And once the transaction is done, the machine state reverts back to null. In any blockchain, the most important question is how do we ensure that all of us agree on the fact that there is a single chain? So this is in effect solving the consensus problem with potentially faulty nodes, which could be faulty in a Byzantine sense. They could be malicious. How do we ensure that? So unlike Bitcoin, what we have seen is Ethereum maintains a tree, kind of a DAG of blocks. We also maintain a list of owners. So that is also maintained. Right. So we also maintain, uncles and, great uncles and so on. But still there is no confusion in terms of the real blockchain, which is a path in the tree. The reason is it is the path with the maximum cumulative difficulty, and we are guaranteed that there will be only one such path. This is clearly the hardest to mine. And given the fact that this involves the maximum amount of proof of work, this is the hardest path, and nobody will have any doubts on the fact that this is the hardest. And this has required the maximum amount of computational effort. So it is possible to prove that if 50 plus epsilon percent, it's colloquially called 51% of the computational power is honest, then there will be no disagreement on this path. So what are the rewards? So in Bitcoin we had a reward for miners. But a problem with Bitcoin was the maximum amount of Bitcoin that can be generated was fixed. In this case, it is not fixed, right? It can be very high. So block's reward is 5 ether, if which you actually see is a lot, given the fact that the ether is 10 raised to power 18 way. It is credited to the address of the beneficiary. And as I have mentioned earlier, the owners also get a consolation prize. So two owners are maintained, and they are the ones who get the consolation prize, which is 1 by 32th each of the block reward, right? So this is what they get, right? Typically, when a block is successfully mined, the owners also get something. So now let's come to the proof of work, right? So in any blockchain kind of system, the proof of work computation is kind of its key. So what was observed in Bitcoin? So you need to understand that Ethereum came much later, so it had enough time to actually see what is wrong in Bitcoin. So some of the things, some of the design principles for the proof of work function was that as many, it should be accessible to as many people. It should not use a custom algorithm or something that somebody with a certain hardware can only do. Furthermore, what people started doing with Bitcoin is that they started fabricating their own custom ASICs and FPGAs. So the way that the designers wanted to generate a function is that it should be ASIC hard, in the sense that there is no great benefit of using an ASIC. So when does the benefit of using a custom chip come? When you can break it down into many parallel components. But in general, it should involve, the algorithm was made in such a way that it has a lot of sequential steps, so it is very hard to efficiently parallelize it. Furthermore, it had a lot of memory accesses, so which also ensured that you would need a large amount of memory, and so larger systems are unlikely to help, right? Because nobody would have that much of memory. So this idea was that you make it general purpose, ensure that you don't have adequate parallelism. That will make the algorithm ASIC hard. So the proof of work algorithm that came out of all of this was called ethash. So the idea of ethash is like this, that we scan all the block headers. So you don't have to scan it from the genesis block, but you can scan it from a checkpoint. And then we kind of hash those values and you compute a seed. So the seed is what creates the dependency between the previous blocks on the blockchain and the block that you want to mine and insert. So this still involves order one amount of work. From the seed, we generate a cache of pseudo random data, which is typically 16 megabytes, right? So you can generate this from the seed, kind of run a pseudo random number generator, generate all this data, and from this you generate a data set, which is a subset of this. I'm sorry, which this, it's not a subset, but the data set uses this, and the data set is large. So I stand corrected. The data set is large, it is several gigabytes, and this is what makes it hard to run a parallel program or run this on an ASIC or run this on a system with a lot of memory, because mining was made difficult. So every 30 to 100,000 blocks, so this keeps on, changing, evolving in a certain sense, the data set is updated. So the data set is updated, but otherwise it remains constant for a, reasonably large chunk. So the data set is of the order of gigabytes. So if you would go back to the fields in the block, you would realize that there were two fields that we had discussed, and we hadn't said much about it. We just said that we'll use it in the proof of work. These two were the mix hash and the nonce. So what we do is that we take the header of the block, we compute a random nonce, we take a random slice of the data set. So this random slice of the data set is actually the mix hash, right? And the data set is this big thing that we generated. So what do? We take a random slice of the data set and mix hash comes out of it. We generate a random nonce. We take all three quantities, the header, the nonce, and the random slice. Then what we do is we compute multiple rounds. So we do this multiple times, and every time we compute a hash. And the final output is like a hash of hashes. It's like a compressed digest, right? Where we have taken the data and we have kind of mixed it several times. In each iteration, we have, of course, used the same random nonce, but we have taken different slices of the data set. So this is important to understand, that 5 is essentially running step 4 several times. The nonce remains the same for the entire process, but the random slice changes. So by changing the random slice several times, keeping the nonce the same, we finally arrive at a compressed digest. So those who are familiar with cryptographic and hashing algorithms will realize that they also work in a similar way, which is that we keep on data, keep on mixing and kind of uh, permuting it for several rounds. So this is kind of similar in principle, but of course the way it works is quite different. But the output is that finally we kind of have a master hash that I'm calling the compressed digest. So how do you verify that this is indeed the proof of work? The way that you verify is that the digest has to be less than equal to a threshold. And the threshold is a function of, is a linear function of 2 raised to power 256 divided by the difficulty. So we have seen the difficulty before. So now just look at it. Higher is the difficulty, lower is the threshold. If the threshold is lower and the digest is kind of randomly distributed, it will be harder for any random nonce to lead to a digest where this will be satisfied. If the difficulty is very very high, the threshold will be very very low, and if the threshold is very low, then the probability of finding a nonce whose digest will be between, let's say, 0 and the threshold, that's going to be quite difficult. And the function is so complex, it's quite hard to kind of work backwards where you fix the value of a digest and work backwards and find out what's the value of a nonce. So pretty much we have to guess random values of a nonce and you have to be lucky, right? So that's the key idea. So the point is that the difficulty basically determines how long on an average it takes to mine a block. Mining a block means what? Finding the mix hash and the nonce such that this condition is being satisfied. So the way that the Ethereum algorithms, Ethereum designers have coded their system, it is that the difficulty gradually increases with time. And the reason is quite simple. The reason is that over time, computational capability increases, right? So our processors get faster, we get more memory on chip, and our memory also becomes faster. So the same difficulty that we had, we can't have it again, otherwise, it will become very easy to mine blocks. And the easier it is to mine blocks, the harder it is to ensure that we still have the view of a single chain. So that is why there is a need to keep the difficulty high. So the difficulty also keeps increasing with time, right? So the difficulty, in fact, of a block is a function of the difficulty of its previous block, right? So it increases. Verifying, as you can see, is quite easy. Any nonce that leads to condition 6 getting satisfied, which is this, essentially satisfies the proof of work. We'll have many such nonces. That's okay, as long as we can find a nonce. And of course, we'll have the mix hash value. As long as this holds, we know that we are done. So, as many of you know, would have seen in this case, the verification is kind of probabilistic. So, it is not giving any party any distinct advantage, unless, of course, it can. So, you can, in principle, take many values of nonsense and run it in parallel. So, that, of course, can be done. But the thing is that it is still ASIC hard because for even running one instance of it, you need a lot of resources. And it's not possible to run maybe more than two or three on a single ASIC because we'll run out of area. But of course, if I have a supercomputer, I can do that. But then again, the algorithm is biased towards parties that have a lot of computational power. So we are not saying that 51% of the parties have to be honest. We are saying 51% of the holders of 51% of the computational power has to be honest. Types of smart contracts. So, well, we can have a lot of smart contracts. So, of course, let me start from the bottom. We could have cryptocurrency. Ethereum, the nice thing is it has built in support for accounts. So, it makes it a default choice. Not only for currency, but anything which is tradable. We can use the internal proof of work mechanisms to generate pseudo random numbers, can easily be done with the mix hash. We can use it as a data provenance mechanism in the sense that we can use it to provide news feeds, current time, and so on. And everybody would know that a given node has provided something. And you can always, later on verify it. So if it turns out to be wrong, we can kind of discard a certain node. So the good thing with the smart contract and blockchain mechanism is that it is the responsibility of the community to enforce that contracts hold, contracts are executed, and kind of the world state is updated honestly, subject to this 51% criterion. So now, sorry, I missed this slide on scalability. So the issue is that the rate of transaction commit, as we have seen in Bitcoin, is quite slow. So it takes 10 times 6, 60 minutes to finalize a transaction. In Ethereum, it's in seconds to minutes. But we can still make it faster. So what we can do is we don't have to store all the blocks and transactions. We can store checkpoints. So we have seen that. We can periodically checkpoint the world state try in the sense if I'm a new node, I want to verify that the world state is correct. I don't have to start from the genesis block. I can start from the previous checkpoint. Inactive nodes that are not active can be thrown out. We can of course create a hierarchical structure where we divide the entire network into sub-networks. Each network computes its own limited chain. So these are known as shards. So this approach is known as sharding. And then, these lightweight chains are finally joined. So this is possible. We can create a hierarchical setup to do it, right? This is indeed possible. well, smaller lightweight chains are made into a bigger chain. So of course all of this is possible. So this has rendered Ethereum quite practical, quite scalable, and quite popular as of today. These are the references. So the main reference is of course Ethereum project yellow paper. So this is always a document in progress. So currently our proof of work is kind of computational proof of work. So Ethereum is moving to Ethereum 2, which will be a proof of stake based proof of work. So once that comes, again, maybe another video is due from my side. So the yellow paper is basically for implementers. It's reasonably technical. If you want something lighter, you can go to the beige paper, which is an easier read.